Hello, I'm Shaun Stevens from the University of East Anglia, and welcome to this short video about complex numbers. For some of you, this will be the first time you've come across them. For others, you'll have studied them a little bit before, but hopefully there'll be something for all of you. So, complex numbers. What are they? Well, before that, I would ask, why are they? So, in other words, don't we have enough numbers already? Well, I think the answer is no. Because some equations don't seem to have solutions. For example, quadratic equations. So you will all know that if we have a quadratic equation, we can write down the quadratic formula. Here it is. But that only makes sense if the number inside the square root, this b squared minus 4ac, is non-negative. If it's negative, we can't take the square root. It just doesn't make sense. And you see that, because, for example, if you draw a graph of one of these quadratics, then sometimes it won't cross the x-axis, so there are no solutions. Well, if we want there to be solutions, well, then we're going to need to invent some new numbers. So, inventing new numbers might seem like a strange thing to do. Is this something we've ever done before? Well, the answer is yes, repeatedly. So, we started with natural numbers. To a certain extent, we invented those already. By abstracting from what we see. So they're the counting numbers, 1, 2, 3, and so on. But quite quickly you find that those are not enough. For example, if you want to share 8 cakes between 6 people, in modern language you end up needing to solve equations like 8x equals 6. And so for that you need fractions, rational numbers. So numbers like 6/8, which of course is the same as 3/4. Is that enough? Well, now suppose you start measuring lengths. Okay, well, Pythagoras' theorem tells us how to work out the length of a hypotenuse of a right-angled triangle. And if 2 of the sides are length 1, well, then the hypotenuse has length the square root of 2. And that is not rational. So we need even more numbers. And in fact, if we want to measure lengths, we need all sorts of numbers. We need some square roots, we need cube roots, we need pretty much anything. Okay, now there's something that I've sort of missed out, but historically it really did come later. What about if we want to solve equations like x plus 4 equals 1? Okay, so this is something which, if you're going back to Greek times, this just didn't make sense. If you asked to what number, if you add 4, do you get 1, they'd have said, well, there are no solutions. Nowadays, we say there are solutions, okay, because minus 3 is a solution. But that's a number that we've had to invent. Okay? And so now we put all these numbers that we've invented and we get the real number line, which you'll be familiar with. So we've invented real numbers and there's lots of invention as we're going along. And now what we're going to do is we're going to invent another new number. And the number we're going to invent is a number which squares to minus 1. Okay? Okay, it's called I. I is for imaginary. It's a really unfortunate name because it's no more imaginary than the number minus 1 itself is imaginary. You'll never see minus 1 of anything. So it's no more imaginary, but call it I. So when did this first come up? Well, this first came up in 16th century Italy. This chap, Cardano, was writing down how to solve cubic equations. So he was the first person to write it down, though not the first person to have solved them. And in order to do that, he found that he had to deal with square roots of negative numbers, and he really didn't like it. So here's a quote which you can read. So what he does is he multiplies some negative square roots, but he uses some words. He says, dismissing mental tortures. Okay. And he talks about this in terms of arithmetical subtlety, and he talks about it being useless, except that it ends up giving him the right answer. Okay, so it's kind of a thing that he doesn't understand what he's doing. So not long after, another Italian called Bombelli really put this together in a better way, in a more formal way. But it was actually a very long time before people accepted, so mathematicians accepted these numbers, as had happened before that with negative numbers. Okay, so what have we done? We've invented this number, I, such that I squared is minus 1. And is that enough? Because why were we doing it? We wanted to be able to make sense of a quadratic formula. Well, if we've got numbers, we should be able to do arithmetic with them, add them, multiply them, and so on. So, for example, we should be able to multiply our new number I by anything we like. So, for example, we can look at the number 2i. And the number 2i, if I square it, well, the normal rules of arithmetic will tell me that I can square the 2 and then square the I. But I squared is minus 1, and so this is 4 times minus 1, which is minus 4. So I also have a square root of minus 4. So 2i is a square root of minus 4. And in fact, more generally, whenever I have a real number d, which is greater than 0, I can do the same sort of thing. So I can look at the square root of d, which is a real number, that makes sense. I can multiply it to my new number that I've invented, I. And then if I square that, I get minus d. And so now all negative real numbers also have square root. And now, well, that's enough to make sense of this square root. So for example, going back to our equation, our graph, which doesn't cross the real axis, so which seemed to have no solutions. Now, if we just substitute into the quadratic formula, we get 2 plus or minus root minus 4 over 2, but we've got a number which squares to minus 4. It was up here, it was 2i, and so I can put that in there, and I get my solutions, which are 1 plus or minus I. So now we seem to be able to make sense of any quadratic formula. And to do that, we've had to invent the number I and then use also the expected rules of arithmetic. Now we're ready to really define what the complex numbers are. So, what are the complex numbers? Well, the complex numbers are symbols. Okay, they're symbols of the form x plus yi, and we'll usually call it a z, where the x and the y are real numbers, so numbers that we know already. Okay, so now we've got these symbols, these complex numbers. Now we want to be able to do arithmetic. We want to add them and multiply them and so on. Before that, there's something else we have to do. So remember when we see fractions, we saw things like 6/8 and 3/4 are actually equal, even though they look different. So, question is, can the same thing happen with complex numbers? Can we have complex numbers which look different, but actually we should think of as being equal? Well, fortunately, the answer to that is no. Okay, so this is the first thing we have to do. We need to say when are two complex numbers equal? And the answer is it's when they look equal. So if we've got a z, which is x plus yi, and a w, which is u plus iv, so if the two complex numbers are equal, we need both the x part, so that's called the real part, and the y, these are called the imaginary parts. We need these to be equal. So that's what it means for complex numbers to be equal. They just look the same, and then they're equal. Addition. Well, addition, we might guess, we can just add together the bits which aren't with the I, and then add together the bits which are with the I. What about multiplication? Well, multiplication is actually not so difficult either, and this is again something which is actually familiar to you. Why do I say that? Well, if you had some mixed numbers with surds, so 1 plus root 2, say, and another number like that, you would know how to add those and how to multiply those. And when you multiply them together, you expand it out, and you would need to use that root 2 times root 2 is 2, and you would simplify it, and that would give you the answer. But it's the same thing here. We multiply out, and we use the fact that I squared is minus 1. So here I've got x plus yi and u plus vi, and I'm going to multiply this out. So I get an xu and an xvi and a y, and I'm going to put the I at the end just to be consistent. And finally, yvi squared. And now I use that I squared is minus 1, and I substitute that in. And what do I get? Well, so that becomes a minus yv. I'll put it together with the term at the beginning. And then we get the term with the I. And here I've written this number as, so this is some real number plus another real number times I. So that's exactly in the form of a complex number. So this is a complex number. And so here it is written out. There's the expression. So now we know how to multiply two complex numbers. So an important thing, so this is we've been defining things. An important thing is that we can still do arithmetic with these, and it works in the way we expect. Okay, so what do I mean? I mean that this obeys all the usual rules of arithmetic. So, for example, if I've got Z and W, which are complex numbers, then if I multiply them together, it doesn't matter which way I multiply. And similarly, when you add them together, it doesn't matter which way you add them. And if I add another complex number as well, so as well as having Z and W, I have another one, let's call it T, then I can also do things like multiplying out brackets. So Z times W plus T is the same as ZW plus ZT. Okay. So now we've seen the definition, we've seen that they obey the usual rules of arithmetic. Let's do some examples. Suppose we want to look at 5 plus 2i times minus 3 minus 4. Okay, so let's multiply this out. So we start off, we will do the things which will give us just real numbers. So that's going to be the 5 times minus 3, so that's minus 15. And the 2i times the minus 4i. So 2 times minus 4 is minus 8, but I squared is minus 1. Minus 8 times minus 1, that's plus 8. And then we'll do the bits which will have i's in them, so the imaginary parts. So we've got a 2i times a minus 3, so that's a minus 6 lots of I. And over here, if I do 5 times minus 4i, 5 times minus 4 is minus 20, so I get minus 20i. And now I can simplify this, minus 5 plus 8, that's minus 7. Minus 6 minus 20, that's minus 26, so that's minus 7, minus 26. Okay, so that's multiplication. Now, it turns out we can also do division. So here's a division example. So suppose I wanted to do 5 plus 2i divided by minus 3 plus 4. How are we going to do that? Well, again, this is something of the sort you've seen before. So if you had an expression with surds, with a 1 plus root 2 in the denominator, you would know how to clear that denominator by multiplying by 1 minus root 2, so that you get a difference of 2 squares in the denominator, which will then simplify to give just an integer. But it's exactly the same thing here. So what we do is we multiply top and bottom by, we take the number that's in the denominator and we change from having plus 4i here to a minus 4i. So there's a special name for this. This is called a complex conjugate number. So we multiply top and bottom. And now, well, the top, well, because of the numbers I've chosen, on the top, we just have the calculation that we did above. So that's nice and easy, minus 7 minus 26i. And what about on the bottom? Well, on the bottom, we've got the difference of 2 squares. So we get minus 3 squared is 9. And then we get 4i times minus 4i. Okay, so 4 times minus 4 is minus 16, but the I squared is minus 1, so we get plus 16. And notice, this is really rather nice. We're getting a sum of 2 positive things. Okay, and so we're definitely not going to get 0 in the denominator. And that's quite key. That's why we can always do division. Okay, and this simplifies. So, of course, 9 plus 16, that's 25. And so then I can write this as minus 7 over 25 minus 26 over 25. Okay. And we can also square numbers, we can cube numbers, we can do any sorts of arithmetic that we want, and this is something that if you've not done it before, you should have a practice with. Okay, so those are some calculations. What about solving equations? So we can also solve some equations. So here, for example, is an equation. We could look at minus 3 plus 4i z plus 1 plus 2i is equal to 6 plus 4i. And how do we solve that? Well, it's just in the normal way. So we put the z's to one side, we put the numbers to the other side, and then we simplify. So here we're going to keep the z and its coefficient, which its coefficient is the complex number minus 3 plus 4i on the left. We're going to take the 1 plus 2i over to the right, so we get 6 minus 1, which is 5, 4i minus 2i, which is 2i, and so what do we get as our answer? It's going to be z is 5 plus 2i divided by minus 3 plus 4i. Okay, and so that's the answer. It doesn't look like a complex number yet because we're dividing two complex numbers, but we know how to divide two complex numbers, and you can do that. And in fact, so I've chosen the same numbers as I had before, so we've actually already done this calculation. It's minus 7 over 25, minus 26 over 25. Okay, so here's another example of solving equations. So we started off with the problem of not being able to solve quadratic equations. So let's see, can we do quadratic equations? So let's start off with a simple one. Let's look at z squared is equal to 7 plus 24i. So how are we going to solve this? Well, our z has got to have the form x plus yi, and if it does, then we can write down what z squared is. Okay, so it's x plus yi all squared, which is multiplying out x squared plus we get the cross term in the middle, 2xyi, and then we get the term at the end, so we'll have a y squared and an I squared, and the I squared is minus 1, so that's minus y squared. Okay, so if I substitute that back in, we need, if we want to solve our original equation up here, we need, so substituting in for z squared, we need x squared minus y squared plus 2xyi is equal to 7 plus 24i. And now, fortunately, we know when two complex numbers are equal. They're equal when both the real parts here at the beginning are equal and also the parts before the I, so the imaginary parts are equal. So that gives us now two equations in x and y. So what we would write is we would write comparing real and imaginary parts. We get two equations. So the first one is x squared minus y squared is 7. And the second one is 2xy equals 24. So we have these simultaneous equations. And we know how to solve simultaneous equations, even though we've got powers in them. That's something that you can go away and do. Indeed, is part of the exercise for you to do, is to finish off this question and actually solve this equation. Okay, so we could do lots of arithmetic. That's really great. One word of warning here with complex numbers. Beware the square root symbol, and in particular, don't ever write I is equal to the square root of minus 1. Okay? This is something that Cardano did in the 16th century. He was writing the square root of minus 15. He didn't really know what he was doing there. And he was lucky it worked out. So why not? Well, here's the reason why not. You might make this mistake. So we start off with minus 1. We know minus 1 is I squared. And I squared is the square root of minus 1 times the square root of minus 1. Okay, but square roots, that's fine. If you've got a square root of a times the square root of b, that's the same as the square root of ab. So this is the same as the square root of minus 1 times minus 1. Okay, great. Well, minus 1 times minus 1, what's that? Well, that's plus 1. So this is the same as the square root of plus 1. But what's the square root of plus 1? Well, we know that. It's 1. So we have just proved, apparently, that minus 1 is equal to 1. Okay. Of course, that doesn't work. And the reason it doesn't work is because of ambiguity in the square root symbol. So when we have a square root of a positive number, we always mean the positive square root. But when you have a negative number and you look at its square root, which one do we mean? Minus 1 has two square roots, plus or minus r. How can you tell which one is which? There isn't a positive one anymore because they're not real numbers. So the mistake kind of comes here. you can't use that the square root of a product is the same as the product of the square roots when you're dealing with complex numbers anymore, because there isn't a single square root and you can't tell which is which. Okay, so that's the end of the introduction. So a few things for you to take away and think about and do. For those of you who are going to be coming to the follow-up session, if you could do these, have a think about these before you come, and then we'll talk about some of these questions when you come. Okay, so the first thing is try some arithmetic. Actually try doing some. So here are some examples that you could try. Hopefully you will find these all okay. So one of them here, this is the one that we started. But you can invent your own as well. Okay, so you can do any sort of arithmetic you want. The one at the end here, this is a bit of a challenge. Okay, you might find that one quite tricky. Okay, certainly if you use the methods that we've been looking at today. But if you know other methods, still try it using what we've seen today. Second thing. Okay, so we know about positive real numbers and negative real numbers. We know about how we can put the real numbers on a number line. We can talk about when one real number is bigger than another. Okay, and we can see that geometrically on the number line. It's further to the right. How does that work with complex numbers? So, for example, if I give you two complex numbers, can you tell me which one's bigger? And how should we picture the complex numbers? Where should we be thinking of? Okay, so we started this off by thinking about needing some new numbers. Okay, we were looking at square roots, we were looking at the quadratic formula, and we needed to invent some new numbers to be able to always have a solution. Okay. Have we done enough? Okay. Or do we still need to invent more numbers? Are there still equations which don't have solutions? And finally, and the picture at the back here might give you something to look at, what are complex numbers actually used for? Okay, so I've said what they are. Okay, so it's great we get solutions to equations, but what are they used for? What do they connect to within mathematics? What do they connect to outside mathematics? Where do they come in useful? And that's something, again, that we'll talk about. So that's it. Thank you very much for listening, and hopefully I will see some of you at the follow-up session.